Hi, so my name is Shomik. I'm a third-year PhD student at Stanford, working in the info lab with Mateza, and I'm going to talk about Weld, which is the system we've been working on for accelerating data science. So the motivation for this project is that modern data applications kind of combine many disjoint processing libraries and functions. So if we just take like the Python data stack, for example, a typical application will load some data using Pandas, maybe train a machine learning model using scikit-learn, and maybe do some numerical processing with NumPy. And on one hand, this is really great, right? Because you get to leverage the work of thousands of people across the globe who've never met. They're all implementing like the best algorithms in each of these domains, and they just all kind of seamlessly work together in some sense. But a kind of negative of this is that there's no optimization across functions, right? You're not trying to buy into this one framework. You're taking these individual libraries and you're stitching them together. And that actually leaves a bunch of performance on the table, the fact that you can't optimize across individual functions in these libraries. Okay, so how bad is this problem? How bad is it that we can't optimize across these disjoint function calls? So it turns out that the growing gap between the time it takes to access the memory and the speed of our CPUs and all these computing devices that are coming out is making the traditional way of combining functionality much worse. And specifically, the way that we combine functionality today is just by making function calls. So I have a super simple example here. We're using Pandas to parse the CSV, then drop some null values, and then compute a mean using NumPy. Right? So I just want to point out that each of these functions in Pandas and NumPy are written in C. So this isn't like Python code that's executing. These are like pretty optimized functions. But if you kind of look under the hood for what's happening here, you have some data sitting around in memory. You call this parse CSV function, which like walks through all your values and produces a new result. Then you call this drop NA thing, produces another result, and then finally you get the answer that you want at the end. And it turns out that doing this repeated accesses instead of doing kind of the obvious thing that you would do in something like C, which is writing a single loop that does all these things on each element, causes up to 30x slowdowns in applications using NumPy, Pandas, even things like TensorFlow, which are written in C++ and have these like specialized compilers, compared to sitting down and writing an optimized C implementation, which is kind of what we're considering to be bare metal performance here. So there's a ton of performance left on the table when we're using these existing libraries. So this is kind of the state of the art of data science today in some sense, right? You go and install something using pip, and you stitch together all these libraries to kind of get the job done. When you have something working, you observe all these performance issues and pipelines, even if they're composed with these fast data science tools. And then you hire some engineers to optimize your pipeline and leverage through hardware. So even at Stanford, we have like people who do machine learning and some people who work on like systems. So machine learning people come up with these algorithms, they write something cool up, and then the systems people come along and like write a little C implementation for them, so they can better interpret that data science fast. Right? So that's kind of where we are today. Weld's vision is that you take that first step and you get bare metal performance for data science out of the box. That's kind of what we're going for here, right? You install some pip package, and these optimizations kind of happen automatically, and you don't really need to spend that much time like squeezing more performance out of your hardware. Kind of just get it without any changes to the API or to the code that the data scientist has to write. Okay, so Weld is this optimizing runtime that kind of tries to achieve this goal. Okay, so kind of to exemplify the performance that Weld can give us, this is like a really simple result. We're like filtering some data set, computing a linear model, and aggregating a few indices. This is using NumPy and Pandas, which is, again, written in C. So if we just run this natively using standard Pandas and NumPy implementations, this takes like like tens of seconds, like 50 seconds or so. Using Weld can actually look at the entire program and kind of generate code, kind of like a JIT compiler for each function. So just with this code generation, you get like a 3x speed up because of things like SIMD instructions and like other compiler optimizations. If you're not using a result, it eliminates that result, and so forth. Weld can also fuse individual calls into like a single loop. So in that example we saw before, we were making these repeated passes over the data. Weld can kind of see that you're doing that and fuse things into like a single loop within each library. So it'll do it for NumPy and do it for Pandas. And that fusion kind of gives us like an 8x speed up over the native implementations. Kind of the magic of Weld comes from the fact that you can actually optimize across these libraries as well. So if you're doing something in NumPy and Pandas, it can take those two computations and kind of fuse them together. So you get kind of one end-to-end optimized program. And that gives us a 29x speed up over the native implementation, right? So we're running this in under a second, and we started with around more than like 50 seconds here. And finally, I'll talk about how this kind of happens a bit more later in the talk. But Weld is a purely parallel runtime. So anything that you can express in Weld, you can actually parallelize to take advantage of multiple cores in your machine, for example. So if we enable multi-threading on a single, on a 12-thread machine, we get a 180x speed up with no changes to the application compared to the native implementations here. This is from things like limiting those like cross-library memory movements, co-optimizing across library calls, generating vectorized code, and all that good stuff. So overall, Weld kind of looks like this. There's some common runtimes, that's what Weld is. And you have these kind of domain-specific libraries, such as SQL, machine learning, graph algorithm libraries, that all kind of target Weld. And then Weld then generates code for these parallel, basically, hardware platforms. So I'll mostly talk about CPUs today. We also have a prototype GPU and FPGA implementation. So if you're interested in those, you can come find me in the office hours to discuss those more. Under the hood, Weld kind of looks like this. So kind of the core of Weld, there's this IR. So an IR is just like a small programming language. And it's a programming language that like people aren't supposed to write. It's actually something that you generate programmatically from libraries. And that happens via this runtime API. And I'll discuss both of these pieces in more detail. But you generate this IR, and once you have like these little IR fragments coming from individual libraries, you can run an optimizer on it, and then use a backend to generate like LLVM and then assembly code. And then you actually pass your data into that kind of compiled binary, and that's what you're running your application against. Okay, so for the rest of this talk, I'll discuss the runtime API, which is how applications kind of speak to Weld. And more specifically, it's how libraries speak to Weld. So kind of one of the main tenets of Weld is that applications themselves don't have to change. You kind of change the implementation of the library. The user-facing application API doesn't need to change. Then I'll talk about Weld's IR, which is how applications express computation. I'll go over some results, and then we'll do a quick demo. Okay, so Weld's runtime API uses lazy evaluation to collect work across disparate libraries. I think this picture kind of sums it up. You have some user application that's making all these function calls into different libraries. We call it lib1.f1, lib2.map, lib2.f2. These are individual calls, and like regular Python, they would kind of fire off one at a time. You pass the result of one call to the next one. You get something back at the end. With Weld, each of these calls is actually emitting a little fragment of this Weld code. And that Weld code is kind of communicated to Weld using the runtime API. So internally, Weld is kind of building up a computation. And when you do something like print your result, or you want to write your result to disk or something, basically whenever you need to actually look at your result in some way, Weld kind of knows that you need to do that, and it'll combine those individual IR fragments together into an optimized program. And it'll run its optimizer to do these things like fusing loops. And then it'll combine it to machine code, and that's what the data in your application actually interacts with. Okay, so in a little bit more detail, without Weld, this is kind of the world you're doing, right? So here we're computing squares, which is just a map, and sum, which is a reduction in a square root. So this is similar to the picture we saw earlier. We have some data sitting around in memory. You call this map function, and then you produce a new array called squares. And then you call reduce and square root, and you get the final result. With Weld, you have this Weld object thing that is kind of internally building up a computation. So here you're just storing the fact that you're going to run a map, followed by the fact that you're going to run a reduce, and then you have this square root. And when you print out the sum or whatever, you get this optimized program. And you're kind of just producing this one single sum. You're not producing these intermediate results. So you evaluate the program once, and you get better performance because you don't have to allocate large chunks of memory or produce these results that you're never going to look at. Okay, well, the second component is its IR, and this is actually how you express the computations that you want to do. So the IR is kind of designed to meet three high-level goals. The first goal is just generality. So we want to support a diverse set of workloads. People are doing everything from machine learning to graph analytics to SQL and their pipelines today. So we want to be able to support all of these things. And we also want to be able to support like nesting of these things, right? So if for every element you want to run like a feature extraction routine or something, we want to be able to support that. Second, we want the ability to express optimizations. So Weld's kind of goal is to be able to run things like loop fusion or vectorization. So we want the IR to be able to express these optimizations. And the final goal is to be explicitly parallel and to target parallel hardware. And this goal just comes from the fact that our hardware is getting increasingly parallel. So designing a language like this in 2018 that doesn't target parallelism seems kind of strange. So parallelism is a top-level goal of our IR. Okay, so internally, the IR is actually really simple in some sense. There's only two main constructs. There's other things like arithmetic and if statements and all that basic stuff. But the crux of the IR is really these two main constructs. The first one is this parallel for loop. So this is just a for loop that always iterates over the data set in parallel. And the second construct is this thing called a builder, which are these declarative objects for producing results. So what does that mean? It means that within the IR itself, you're not actually specifying how you do something in some sense. Right? So a builder might say something like append items to a list, or compute a sum, or compute a group by, or make a dictionary, or something like that. But the builder isn't specifying how these things are actually implemented. And what this means is that you can actually implement them very differently on different hardware. Builders also have this additional restriction that you're not allowed to read from them until you're done with all your writes to them. So slightly technical, but basically what that means is you don't have to worry about things like locking, for example, in the IR, right? You don't have to worry about, oh, is this builder like locked when I'm iterating over it in parallel? Can this thread access it while this other thread is doing something on it? It just makes doing these optimizations like loop fusion extremely simple over the IR, right? You can just implement them as a set of pattern matching rules, and then the backends, which are actually generating low-level code, will take care of things like synchronization and actually implementing these builders. Okay, so that's this right before read semantics. And we found that just these two kind of core constructs can capture everything from relational algebra to the functional APIs of Spark. So map, reduce, group by, all this great stuff. And Spark itself is, built, there's many libraries that use just the functional APIs of Spark. Then linear algebra, and then most importantly, we can also capture a composition of all these things. Okay, so just an example of what this IR kind of looks like. Here are some functional operators using builders. Okay, so this is a map function. So you're taking this function f and applying it to every element in data. So this builder, we're just creating a new builder here. This is an appender, which is just appending items to a list. So note that we're not actually specifying how items are appending to a list, right? So there's actually a lot of fluff under the appender that goes on because you want to do this in parallel. There's some synchronization you have to do and so forth, but we're not specifying how that happens at the IR level. But this for loop is occurring in parallel, and we're doing a merge operation. So a merge just means put something in the builder. So this is a write into the builder. So we're just merging f of x, which is what the map does, into the builder. And then the result is what kind of reads the result out of the builder. So this is saying that we're done with all our writes, assemble like the pieces that you have on multiple threads or whatever, and give us back a result. So that's kind of what kind of commits the builder and gives you back your final list. To implement a reduce operation, it looks very similar. We're just changing the builder kind from appender to merger. And a merge is just a builder that takes some identity element and a commutative function and kind of merges values into like a scalar or a struct or whatever. And there's a few other builders in the language too. Things ranging from building dictionaries to in-place updates to lists to building groups. Yeah, if you want more details on that, we can talk about it. So some example optimizations that Weld can do. We have this example here where we're computing a map over some data followed by a reduce on the same data, right? So we're traversing over this data vector twice. In Weld, this is kind of expressed using just these for loops. So there's just one kind of unified construct, the for loop, to traverse over data, and then these builders to kind of create results. So instead of making two loops, we can actually identify that, oh, we're doing two for loops over the same data. Let's just apply some pattern matching rule that merges this into a single loop and create 2 results at once. Right? So we have a single for loop, and we just merge 2 results into these 2 different builders. So you're getting your results with a single loop of the data. And you can see here that we support things like vectorization in the IR too. So we're actually using like a SIMD value here to get even better performance out of this program. Right? So the loops are merged into one pass for the data and vectorized. Okay, so this is just a laundry list of other features that we have. It is a research project, but we're working hard to actually make it usable. So one thing that we're really focusing on is if people want to use this, it should be easy to debug. So we have all these great debugging features ranging from an interactive REPL for debugging, a bunch of logging, ability to call into C functions, ability to dump code. We even have syntax highlighting for Vim. So I encourage people to try it out. Okay, implementation-wise, Weld currently has APIs in C and Python, with Java support coming soon. So you can build up these Weld computations using C and Python function calls, and internally it'll do some magic to stitch these computations together. And all the compiler and stuff is kind of hidden away from the user. So there's a full LLVM-based CPU backend with CPU support. The actual compiler itself is written in around 30,000 lines of Rust, which is this nice, safe language with no runtime. But I guess the Rust stuff is kind of hidden away from most users of the system. So really the point of interaction for most users will be able to see in Python APIs. And finally, we have partial prototypes of Pandas and NumPy. So these are just prototypes. And TensorFlow and Spark with Weld kind of integrated into them. So this is like a subset of the Pandas operators with lazy evaluation and a subset of the NumPy operators with lazy evaluation. And all these things are open source. So if you want to try out the actual Weld-enabled libraries, you just need to change an import statement here, right? So if you do import Pandas as PD, you can change that to import Grizzly as GR or whatever. Same with NumPy, you just have to install Weld. NumPy is a drop-in replacement for the existing NumPy distribution. If you want to build your own Weld-enabled libraries or frameworks, there's also a PyWeld distribution, which is the actual API for using Weld. And then all our code is also open source if you're interested in adding new features or building like C-based backends, for example. Okay, so I'm going to talk a little bit about Grizzly, which is our Weld-enabled version of Pandas. So we support a bunch of the popular operators that Pandas includes. Things like unique, filter, mask, group by, pivot table, these operations on series and data frames. And kind of the goal of Grizzly is to give you, transparent single and multi-core speedups. So if you're just to remove your Pandas import statement and put Grizzly in, you should just see, improvements in performance. And we only support a subset of the operators, but it also interoperates with the existing Pandas API. So if you do something that we don't support, Grizzly will transparently kind of convert the data into a format that Pandas understands. And then you can do your stuff in Pandas, and it'll, kind of transparently convert it back. So to kind of see Grizzly in action, I have this example here. It's taken from the Pandas cookbook. So you're just reading some files, and you're cleaning up some zip codes. So you're dropping NaN values, and you're making sure that each zip code is only 5 characters long. So to convert this to something that uses Grizzly instead of Pandas, you add this import statement. We're still using Pandas here to do I/O. But then you just wrap that data frame into a Grizzly data frame, and the rest of your code doesn't change. And you just see a faster runtime. Okay, so if you're interested in using Weld in your own applications, I have some notes on how hard it is to do that here. So in our integrations, there's a fairly small cost to enable Weld integration. So for NumPy and Pandas, for example, it took us around 500 lines of code to set up things like large string data from a format that Pandas understands or something that Weld understands. And then after that, it took us around 30 lines of code to port over each individual operator. And importantly, you can actually incrementally deploy Weld. So you can take like the most common operators and make those Weld enabled, and they'll still be able to speak to the rest of the libraries. You don't have to sit down for a month and convert everything over. Kind of do it incrementally and see if it's having an impact on your workload. Okay, so I'll go through some results. This first set of results is showing that Weld can accelerate existing libraries rather substantially. So on TPCH, which is kind of this standard benchmark that database folks use for evaluating runtime performance, integrating Spark SQL with Weld gave us a 3.5x speed up on these two queries. And this is compared against Spark SQL 2.1, I think, which has this Java native code generation already. And these speedups are basically coming from the fact that we're generating like native assembly code, basically, that's vectorized, as opposed to Java, which is generating Java bytecode. Right? So this speedup is almost entirely from native code generation, because Spark already does like the loop fusion optimizations in its optimizer. For NumPy, on this Black Scholes workload, which is this financial ranking workload, we see a 4.5x speedup. And this is from fusing loops together. So NumPy will, by default, run each loop kind of as it sees it. So if you call np.add, it's going to run through all your data and give you back new results. With Weld, it'll kind of build up the computation incrementally and run everything at once. So that kind of loop fusion gives you a 4.5x speedup on one thread and more substantial speedup on 12 threads. And with TensorFlow on logistic regression, both Weld and XLA, which is this TensorFlow specific compiler, outperform the standard TensorFlow rather substantially by around 10x. And Weld is actually competitive with XLA's performance. So XLA is the specialized compiler that Google has put out for TensorFlow, actually for many of the same reasons that Weld was kind of designed. So Weld is really competitive with these kind of domain-specific compilers as well. Weld really shines on these multi-library workflows, however. So we saw this at the beginning of the talk. This is a data cleaning kind of linear algebra workload using Pandas and NumPy. And here we see 180x speed up on 12 threads over the native implementation by fusing libraries. On this workflow, we're whitening some images and then doing a linear regression. And the whitening happens in NumPy and the linear regression happens in TensorFlow, the two kind of disjoint libraries. By kind of looking at the whole computation together and optimizing over it, you get an 9x speed up over like a native implementation. Both of which are pretty optimized. Both are written in C already. And finally, we also support kind of UDFs. So we have a small kind of wrapper that maps like Scala functions into Weld functions. So this is evaluating a small linear model using a Scala UDF in Spark and generating native code for that. Again, gives us a 6x speed up. And finally, this is just looking at the effect of incremental integration. So here we're just porting one operator at a time for this Black Scholes workload. And kind of the takeaway from this is that the more operators you implement, the better your performance gets. But you still get these incremental gains when you port kind of one operator at a time. This is just kind of some evidence saying that you don't have to like take your entire application and port it over. You can kind of do it incrementally and evaluate whether it's accelerating your workloads or not. Right? So for this Black Scholes workload, you get these incremental benefits with incremental integration. Okay, so I'm going to switch over to a demo now. So this works. Let's just going to connect to this pipeline notebook that's running on EC2. Can people see this?
It's a little small.
Okay. Good. Better? Okay. Yeah, so this workload is basically going to run one of the Pandas tutorials. So all the tutorial is doing is it's cleaning some data. So it's similar to the example that I showed up on the slides before. So this is the main function. So we're just taking some values in a data frame, and we're slicing them. We're replacing some values here, and we're replacing the zeros and codes with NaN. And then we output like the number of unique zip codes in our output. So there's a number of operators here. So think about what happens in Pandas here, right? You're kind of slicing each of these things, and you're setting some of them to 0. Then you're kind of doing this mask, setting them to NaN, then counting the unique things, and then finally getting the length. Okay, so it's like a handful of operators. And the hope is that by kind of using Weld and fusing them together, we get better performance. So we'll just click through this quickly. Okay, so we'll load the data here. All right, so there's our data frame. Now we'll run it with Pandas. So run for around 11 or 12 seconds. awkward thing about runtime, so to wait. Okay, yeah. So that took around 12 seconds to run. We got 246 unique zip codes. Okay, so now we'll run this with Grizzly. So all I did here is I imported this Grizzly data frame thing. This is just because I want to use one thread, so I set some environment variable. And I'm just wrapping the data frame here with this gr.dataframe. So if you look, we're calling the exact same function. So we haven't changed the function that we're running at all. We're just wrapping the data frame in a Grizzly data frame instead. Okay, so we'll go ahead and run that. And that took around 2.5 seconds. Okay, so now we can actually run this with multiple threads. Remember that Pandas natively is a single-threaded framework. So these are kind of like invisible multi-threaded speedups we're getting. So on 8 threads, we do this in less than a second. So we're over 10x faster than what Pandas did native. Let's plot that in a nice graph. All right. Okay, so to conclude, kind of changing that interface between libraries can speed up analytics frameworks by 10 to 100x on modern hardware. And this is just by taking advantage of the fact that you can look at the whole program at once instead of having to run each function call individually. If you're interested in trying out Weld, all of our code is open source. You can either pip install these frameworks, or if you want to contribute, you can check out our GitHub.